All right, so in this video, we're going to be looking at how to solve systems of nonlinear equations in more than two variables. In multivariable calculus, in particular, when you're solving for optimization problems, particularly when you're doing Lagrange multipliers, you often end up with systems of equations that have 3 variables, 4 variables, even 5 variables, depending on how many constraints you have. And so we're going to look at some strategies for solving those kinds of systems. Now, typically, I find that the easiest strategy is going to be involving some sort of substitution ultimately in the end. But your strategies are going to have to be adaptable in order to apply to the individual system that you're dealing with. In particular, because every system is a little bit different. And the main goal is to try to reduce the number of variables that you have in order to get it down to something where you can work with it, eventually to one variable. And so exactly the strategies that you employ is going to depend a little bit on the kinds of equations that you have. But in some cases, you will find that you can add equations together in order to eliminate some of the variables. You can solve using substitution for one or more of the variables and substitute those relationships into the other equations. But always, essentially, the goal is to try to get your equations down to a point where you can maybe set things equal to 0, you can factor stuff out, but you can reduce the number of variables in your equation. Now, in this particular example, we have a minus z in one equation, and we have a plus z in the two other equations. So my first strategy is going to be, I'm going to add the first equation to the second equation, and I'm also going to add the third equation to the second equation, because that's going to get rid of the z for me. So that will give me two equations in only two variables. So x squared plus x plus y minus y squared is equal to, again, the z's cancel. It's going to give me 42. And then in the second equation, if I add the third equation and the second equation together, I get 2x plus y minus y squared. The z's cancel is equal to 8. All right, so that's an improvement. The z's are gone. And one thing that I see in both of these equations is that both of these equations have y minus y squared in them. So what I'm going to do is I am going to put a minus sign through the second equation, flip all the signs, and then I'm going to add these two equations together, and that's going to get me x squared. X and minus 2 is going to give me minus x. Y and minus y, 0, minus y squared plus y squared, 0. 42 minus 8 is going to give me 34, I believe. Yes, equals 34. I'm now at a point where I can put everything on one side of the equation because I have only one variable left. And factors of 34 that have a difference of 1, I can't think of any. And so we're going to use the quadratic formula. X is equal to 1 plus and minus the square root of 1 minus 4 times negative 34 divided by 2, which is going to be 1 plus and minus, let's see, 4 times 34 plus 1 is going to be the square root of 137 divided by 2. Not the world's best solution, but it is a solution to our x. So we have two possible solutions for x. And so what we can do from there is we can use one of our previous equations to try to plug that in and get ourselves an expression that we can use to solve for y. So for instance, we had this equation here where there is a 2x in the equation that's linear. So what I'm going to do is I'm going to solve this equation. Again, it's going to be messy, but we can solve this equation, and I'm going to plug in initially 1 plus the square root of 137 divided by 2. And that's going to give me, again, a quadratic equation that involves y only. Again, not attractive, but let's see what happens. I want to flip my signs, minus y, and then I need to move my 8 around and combine it with this. And I'm going to end up, when I move things around, my 2's here are going to cancel, and I'm going to end up with plus 7 minus the square root of 137 equals 0. And then I'll have a second equation that will, when I plug in the negative version of this, will be exactly the same, but with a plus in front of the square root instead. And again, I'm going to need to use the quadratic formula to solve this. Y is going to be equal to 1 plus and minus the square root. Actually, let me put this in a fraction already. The square root of 1 minus 4 times this. All over 2. And then I'll similarly have another answer, conceivably, where this is now a plus. Now, if we double check this, 7 minus the square root of 137 is a negative number times 4. 1 minus that answer, I'm going to end up with a positive number under this square root. But on the other square root, I'm not going to get a positive answer, because I'm going to get this expression right here is basically like 18. And if I multiply that by 4, that's definitely going to be less than, it's going to give me a negative number under the radical, basically. So what I'm going to say is this one is out, because it's going to give me unreal solutions. This one, on the other hand, I can go ahead and continue simplifying. So 4 times 7 is going to give me 28, and then plus 4 times the square root of 137. Get rid of that And again, this is going to be a positive value under the radical. Again, it's not an attractive value, but it is a positive value under the radical. And so I am going to get two solutions out of this. If we want, we can estimate these to various decimal places. So 1 plus the square root of 137 divided by 2 is approximately 6.35, blah, blah, blah. And 1 minus the square root of 137 divided by 2 is going to be negative 5.35. So two possible answers. We said that one of these is not going to give us a positive value under the radical. 1 minus 28 plus 4 square root of 137. This number here is approximately 19.8. I'm going to take the square root of that. And then that's about 4.45. So plus 1 divided by 2, I'm going to end up with approximately 2.7259. And and 1 minus that, the square root value divided by 2 is going to give me about negative 1.7259. And then once I have these values for X and Y, then I can go back and I can find my corresponding Z value. We know that my original equation, my original system had this equation in it. And so we can take each pair of X and Y values and use them to solve linearly for Z. We don't have to use the versions that have the squares in them. But the thing to keep in mind is the way that these things pair up. So this set of equations, these two solutions only came from one of our X values. So we kind of have to keep that in mind. The one set of X values actually is not going to work. If I put 6 under here, for instance, that's the one that's going to get me the, I believe, is the one that's going to get me the unreal solution under here. And again, you just have to be careful about the way that you proceed. And then plug those corresponding pairs of values into your X, Y, and Z equation. You should get, at least in this problem, 2 values for Z, because you have 2 values for Y, and only one of the X values gave you your Y value. So you should have, in the end, for this particular example, 2 solutions. So if we assume, I think from the math, that the positive X value was the one that got us the 2Y solution. So that was about X approximately equal to 6.35. And then we have our 2 possible Y solutions. We'll say approximately 2.73. Again, we'll just estimate them. And then also Y equals negative 1.73. Then for the one value for X and the first value for Y, we'll get 6.35 plus 2.73 minus plus z is equal to 3. And so if I want z, I move everything to the other side. 3 minus 6.35 minus 2.73. And I end up with approximately negative 6.08 for one possible solution. And if I put in x is 6.35, boy, am I typing. Yeah, I typed it in the calculator correctly. And then minus 1.73 for my other y value plus z is equal to 3. I end up with z is approximately 3 minus 6.35 plus 1.73 is going to get me about negative 1.62. Again, approximately. We can take more decimal places if we need greater levels of accuracy. And so our solutions in 3 dimensions for this particular example are approximately 6.35, 2.73, and negative 6.08. And then the other one is 6.35, negative 1.73, and negative 1.62. Now, again, when you have 3 equations, you can have many, many more solutions than this. Typically, when you're doing multivariable calculus, textbook problems will mostly try to give you fractions or whole numbers. They're carefully selected in order to make sure that that happens. This particular example I took from a problem that was intended for you to do estimation on using Newton's method in multiple variables. And so the fact that I got crazy answers does not really surprise me because it wasn't designed to give you nice answers. But typically when you're doing multivariable problems in textbooks, you will get nicer looking answers. When you're out in the real world doing real world problems, you won't get nice answers. You'll get lots of nasty garbage like this. But again, the idea here is mainly you want to be methodical about it. The first goal is to reduce the problem from 3 variables to 1 variable, or again, step by step, reduce from 3 variables to 2 variables, and then from 2 variables down to 1 variable if you possibly can. If you have a 4 variable problem, again, the idea is to start finding a way to eliminate one of the variables, work your way down to a point where you have a single variable left, and then you can go ahead and start to come up with solutions for one of the variables. If you get more than one solution, then your process kind of has to bifurcate. In this case, one of our X solutions ended up not being viable as a solution for any of the other variables, so we were able to toss it out. And that will also sometimes happen as you're going through this process. You may find that you get extraneous solutions that have to be eliminated before you can proceed. But the more variables you have and the more kinds of squares and things like that that you have in the equation, the greater the possibility there is for getting multiple solutions, not just 2, but maybe 4 or 6, again, depending on the kind of system that you have.